In this video I'll cover Year 10 Pythagoras and trigonometry applications. So these are the sort of questions that you should say at an A and B level. I'll put some time tags below for those following along with the test preview, and for everyone else I've got some descriptions down there for the sorts of questions these ones are. Question 1 starts with some Pythagoras, but this one's got algebra in it. We can see that this one's an isosceles triangle. These two are the same. So if we run the formula c squared equals a squared plus b squared, where the hypotenuse is c, we'll sub in and we'll find that we've got 22 squared equals x squared plus x squared. What we'll do is we'll collect our like terms, and we might even solve 22 squared at the same time. So we'll have 484 equaling 2x squared. And now I'm just going to switch to the balance method. I'm going to get rid of that 2. So I'm going to divide by 2 both sides, and I'll find that I've got 242 equaling x squared. Now I want to get rid of that little squared. So the opposite to squared is to square root. So I'll square root both sides, and I'll find that x is 15.56 centimeters. Not forgetting your units, because this is a measurement question. In the second one, it looks like we're going to have to do 2 steps here. Obviously, I want to know what the length of x is, but there's not enough information in this right angle triangle here to give it to me. So I'm going to have to put an extra step in. I'm going to call this y, and you can use whatever prime numeral you want, but I'm going to solve for y first, and then I'm going to try and solve for x. So just looking at this triangle up here to begin with, I'm going to go in with my variation of the Pythagoras formula. So a squared equals c squared minus b squared. And the reason that I'm doing that is because the subject of this question is not the hypotenuse. So I'm going to make a y, and then I'm going to have 8 squared minus 5.5 squared. I'm going to use my calculator to work out what that is. So y squared is going to be 33.75. And I'm going to stop at this point. I don't want to work out what y is. Normally I'd square root that to get the answer, but seeing as I've now got y and I'm looking for x, I'm going to run the same formula again. So I'm going to go back to a squared equals c squared minus b squared, because again, this time x here is not the subject, is not the hypotenuse, sorry. So we want to run this variation of the formula. So x squared will be c squared, which is 6.3, minus, and then I just substitute 33.75 straight in. There's no squared here, because remember, y squared was 33.75, so b squared is going to be 33.75. We don't need to square it. All right, this helps us with the accuracy a little bit. Again, I'm going to use my calculator, and x squared is going to give me 5.94. And at this stage, I don't want x squared. I want to know what x is. So I'll square root both sides to get rid of that little squared. And x will be 2.44 meters. And that's my final answer. Question C is another Pythagoras one. This time the subject of the equation is the hypotenuse. So I'll go back to c squared equals a squared plus b squared. But we can see this time that the hypotenuse is a bit of an unusual one. I don't want that 3x minus 4 falling apart. So when I put it in as c, I'm going to put it in brackets. And I'm going to let it just sit there in brackets while I solve the whole equation. And then at the very end, I'll solve for x. So I've got 40 squared, whoops, plus 9 squared. If I use my calculator, I find that 3x minus 4, just leaving it in brackets, is going to equal 1,681. And now I'm ready to get rid of that squared. So balance method, I'll square root both sides. Now the brackets can fall away. And I'll start solving for x. Let's add 4 to both sides. So just balance method now. 3x will be 45. Divide by 3 both sides. And x is 15 millimeters. That's my final answer. The next question is a trigonometry question, and we've got another one of these sides that's got one of these awkward algebraic expressions instead of a number. So what we'll do before we even begin is pop that in brackets so it doesn't fall apart. Now, 26 degrees is our reference angle here. So remembering SOHCAHTOA, so we've got our trigonometric rules. That would make this side the adjacent and this side the hypotenuse. This side's the opposite, but that's irrelevant in this question. So if we've got an adjacent and a hypotenuse, we'll use the cos rule. So we'll begin with the rule cos theta equals the adjacent over the hypotenuse. And we'll start filling it in with the information that we've got. So we've got cos 26 degrees equals the adjacent, which we're going to put in brackets so it doesn't fall apart on us at this stage, all over 12. And from here what we'll do is we'll start to work our way back to x. So let's get rid of that 12 that's skulking around down here. So we'll multiply both sides by 12. And now what we'll have is 12 times cos 26 equaling our 11 minus 2x. I'm not going to put it in my calculator yet, and when I mean that, I'm not putting this in the calculator yet, because as soon as I do that, I'm going to round it and start introducing error. So I'm just going to ignore it for the minute, and now I'll get rid of that 11. It's a positive number, so I'll take 11 away. So now what I've got is 12 times cos 26 minus 11 equaling minus 2x. And now I want to get rid of that minus 2. So we'll divide both sides by minus 2. And now I've got 12 times cos 26 minus 11 all over 2, minus 2 rather, equaling x. And now all I've got to do is put it in my calculator. And my calculator tells me that x is 0.1072, which I think we can round down a bit. So let's round that down to 0.11. Meters technically. It does look too small, but don't freak out. Remember that it's part of an expression, okay? So it was part of this expression up here. So x, it makes sense if it's quite small. That overall distance would be a bit longer, but this is the correct answer. Question 3 is a bit trickier. What they've done is they've given us an unusual looking shape inside a circle. They haven't given us very much information. Remember though that this topic is Pythagoras and trigonometry, so we're only really dealing with right angle triangles, so we're going to make right angle triangles out of this. The information that we've got is that the radius from the center to the outer edge is 8 centimeters, but that's not particularly useful. If I double that though, what I'll end up with is the diameter of the circle, which is 16 centimeters. Now, this interesting shape in the middle, if you have a look at that, I'll remove this for a second, is actually a triangle here that's making up half of this square overall. So if I just change the rules a little bit here, and I say that if I chop it in half, and now I chase this half of the square, I can use Pythagoras to work that out, because I know that this is 16, and it doesn't really matter that I don't know what these are, because that is going to be the same as that. And this is really similar to the very first question that we did. Now, what I'm after is the shaded area of this shape. So this would give me the shaded area in the center of the square, because it still gives me half a triangle. And then all I've got to do is take the other half, the missing part, away from the total area of the circle. So if this is making any sense to everybody, what I'm going to be doing is I'm going to be taking the full circle and then deleting the half that's white. Alright, so let's first of all work out what x is. I know that I need to use Pythagoras, so I'm going in with c squared equals a squared plus b squared. Now, I know the hypotenuse, so I start filling it out. I've got 16 squared here, and both a and b are x squared. If you missed this in the first question, go back and have a look at it again. Okay? And so that means that I've got 128 here, and I'm going to collect my like terms here. Sorry, I've got 256 here, and we've collected my like terms on the right. And now if I jump to balance method, and I divide by 2 on both sides, I'll have that this is 128. I was jumping ahead of myself there, equaling x squared. And this is where last time I stopped, because I don't necessarily want to round this if there's a follow-up Pythagoras question. Now, in this unique example, because the shape at the top is a square, and I'm trying to work out what half the square is, if I square root that, I'm only going to end up squaring it again anyway. I'm not sure if that's making sense, but remember that I've got a square that is x by x. So the total area of this shape is going to be 128 square centimeters, and I want to know what half of that is. Okay, so the area of my triangle that I'm going to subtract away is going to be half of 128, which is going to be 64. And we're just going to leave that sitting here for a minute. Okay, so this is the area of my triangle. Now what I need is the area of the circle, the full area of the circle. And so the area of the circle is going to be pi r squared, which is going to be pi times 8 squared. If I put that in my calculator, is 201.06. And so now I've got my two areas. This one's also in centimeters squared. And so now I've got my two areas. So my total area, my area total, is going to be the area of my circle minus the area of the triangle, or half the square if you like, that I'm subtracting away from the circle. So it's going to be the 201.06, which I've left in my calculator so that I don't have a rounding error, minus, it's a very big minus, minus 64, which gives me the answer 137.06 square centimeters. And this here is my very final answer to this question. Alrighty, moving on to question 4. This is questions about compass bearings, and it's possibly a new concept to a few people. There are two sorts of compass bearings here. There's a true bearing over here on the left, and then there's a northing bearing here on the right. So we'll go through what each of those mean as we do the question. If you're doing true bearings, then the compass will read like a rotation. So it starts up here at 0 or 360. Okay, and this is 90, this is 180, this is 270, back to 360 at the top again. And so if you are traveling on a course of 195 degrees, then you have traveled round past 180 and an additional 15 degrees to this point here. Okay, so we might draw that neatly with our ruler. So we've got a ship that's sailing on a bearing of 195 degrees. That's traveling down like this. And we know that it's traveled 30 kilometers, and they want us to tell it how far west it's finished. So we've got an option here. We can draw a triangle this way. But if you'd drawn the triangle in this direction, that's fine as well. There's no problem with that. Maybe not a rectangle, but if you'd drawn it like that, it's fine as well. So we'll write in the information that we know. We know that this one represents 30 kilometers, and we know that we're trying to find how far west it's traveled. Remember to never eat soggy Weet-Bix when you're labeling this up. And there's another little bit of information that we know as well. In fact, to be honest, doing it the other way might have been a little easier because we knew that this was 15 degrees if you'd drawn your triangle that way. But seeing as we've committed to doing it this way, we know that the difference between this is 90 degrees here, so the difference between 90 and 15 leaves us with 75 degrees. So we've got 75 degrees in here, and now we can start using trigonometry to work this out. So we remember the rule. So we know which rule we're going to use, and we'll label this one up. If this is my reference angle, this one's my adjacent, and this one's my hypotenuse. This is the opposite, but this is irrelevant for this question. So we find ourselves using the cos rule because we've got the adjacent and the hypotenuse, so we'll use this one. And so to answer this, we say cos theta equals the adjacent over the hypotenuse. So cos 75 is going to be x over 30. Now if we rearrange this equation, we'll find that 30 times cos 75 will be x. And at this point, we'll put it into our calculator and we'll find that x is 7.76 kilometers. And because this question is asking for it to be west and it's a compass bearing, I would write W or west on the end of this answer. So this would be my final answer. Just bear in mind that if you had chosen to use the other triangle, so if you had gone this way, then this would have been 15 degrees in here, but that would have made this the subject of the equation, and that would have been the opposite and the hypotenuse. So you may have used the sine rule to get to the same answer, and that's fine as well. It's whichever one you prefer. Let's move on to question 5. This one's got a northing bearing, so these ones will either be called from the north and then a certain number of degrees east or west, or they'll be called from the south, a certain number of degrees east or west. So if we're being called north 40 degrees east, that means I take it from north and I draw in a line that I think is roughly 40 degrees east of that. So the 40 degrees is sitting in here, and that will become my reference angle. This time it's asking me how far north it finishes. So let's put a right angle triangle in. And this time the man has walked 1100 meters and they want to know how far north he's gone. So it's going to turn out to be quite similar to the last one. If this is my reference angle here, this one will be the adjacent. This one will be the hypotenuse, and this one will be the opposite, but that's irrelevant. If we go up and have a look at our rules, we'll again be using the cos rule because we have an adjacent and a hypotenuse. So run cos theta equals the adjacent over the hypotenuse, which means that cos 40 is x over 1100. That means that x is 1100 times cos 40, and then I'll pop that into my calculator and I'll find that the distance is travelled is 842 meters, 0.65 meters north. Now again, if you guys had decided when you did this that you drew your triangle this way and made this 50 degrees in here, absolutely fine as well. Just remember that that would have meant that the north that you were chasing was over here. You still would have known your hypotenuse, but you would have found that you were using the opposite and the hypotenuse, so you would have used the sine rule instead, and your right angle would have been down here. Neither is more correct, it's just whichever way you see it or you draw it on the day. Alright, I'm going to highlight our final answer. Question 5, I've drawn ahead of time. So what we've got here is we've got someone flying their kite, and we haven't talked about angles of elevation or depression at this point, but the best way to probably think about this is if you think about your line of sight, so this is your line of eyesight here, if you're looking straight ahead, if you need to look up, this is called an angle of elevation, and if you look down, this is an angle of depression. So in other words, it's the angle off the horizon. So if we consider this question here, the angle of elevation from a boy to his kite is 81 degrees. That means that it's 81 degrees in here because he's looking up. Okay. If the string attached to his kite is 36 meters long, how high is the kite off the ground? So what we'll do is we'll complete it as a right angle triangle. And we're trying to find how high the kite is. So we're back to trigonometry, and we'll use the rules SOHCAHTOA. If 81 is my reference angle, x is the opposite, the string is the hypotenuse. If I've got an opposite and adjacent, then I'm going to use the sine rule. So we'll go in with the rule, sine theta equals opposite over hypotenuse. Sub in what we know, so sine theta will be Oh, sorry, we know the angle, don't we? Sine 81 will be the opposite over the hypotenuse. That means that x is going to be 36 times sine 81. Now I'll just put it in my calculator, and x will be 35.56. So the kite is 35.56 meters high. Worded question, worded answer, and we've successfully finished it. Last question. This is a pretty long one. This one's talking about angles of depression from a drone. So it's flying above the ground and it's got a couple of targets that it can see. And we need to be careful how we draw this one. So you can draw this in a couple of different ways. I'm going to draw a line to, so its first target is has got an angle of depression of 30.5 meters. So remember that is down off the horizon. So what we'll do is we might make these triangles different colors. So let's make the first one orange. So if it's sighting this with an angle of depression at 30.5 degrees, remember that the horizon of the drone, so that's this line, is parallel to this line, okay? And we might remember that alternate angles between parallel lines are equal. So this angle down here is also 30.5. This is just going to keep the drawing a little cleaner and a little clearer. So what we'll do is we'll finish this triangle here. And we've successfully created one triangle here. We've got an angle, we've got a right angle. And then the second object that it spots is on an angle of a depression of 28 degrees. So that's this one over here. Again, rather than do the angle at the top, because you see the angles would have overlapped, I'll do the alternate angles here, which is 28 degrees here. And of course, that triangle finishes over the top of this orange line as well. Okay, so we've got basically one big triangle sitting over the top of a smaller triangle. Now, the question is, how far apart are the targets? And what we need to try and find is we need to try and find this distance in here. So from here to here. And in order to do that, what I'm going to need to do, so we'll call this one X. What I'm going to need to do is I'm going to need to find the length of the base of the large triangle. Oops. So let's call that one Y. And then I'm going to need to find the length of the base of the smaller triangle. So let's call that one Z. And just so that I know what I'm up to here, I know that the length of X, which is the distance between the two targets, is going to be Y minus Z. So I'm going to have to work out the base of both triangles and then subtract the difference of the length. So let's have a look. We need another piece of information. We're still short. It tells me that the height of the drone is 105, so I can add that in. And now I've got enough information. I've got an angle and I've got a side. I can use trigonometry. So back to the trigonometry rules. So Toa. Now in each case, the reference angle is sitting down here. So this side is going to be the adjacent for both. And I've also got an opposite, no hypotenuse this time. So both times I'm going to be running the tan rule. So I'm going to do the large triangle first. I'll stick with the colours that I stuck with. So purple for the large one, orange for the small one. So let's go. Tan theta equals the opposite over the adjacent. So tan 28 is going to equal 105 over, and remember the big triangle is y, okay? So that one relates to that one, and z relates to the small one. So back to this. Now we need to switch those two, so that means that y is going to be equal to 105 over tan 28. And I've just put that in my calculator, and that is 197.48. We might actually carry a few extra decimals here just so that I don't make a rounding error. So 7628. Alright. And now we need to work out the smaller triangle. So we've got, again, tan, because we've got an adjacent and an opposite. Theta equals opposite over adjacent. This time it's tan 30.5 equals z over 105. Ooh, I've made a mistake there, haven't I? Therefore, it's opposite over adjacent, 105 over z. Do the same switch. Z will be 105 divided by tan 30.5, and I'll just pause and put that in my calculator. And that gives us the answer 178.25463. And now we can solve it. So if we're looking for the distance and we've decided that x is going to be y minus z, then x will be y, which was 197.47628 minus 178.25463. We'll pop that into our calculator again, and we'll find that that distance is 19.2216. So, therefore, the targets are 19.22 meters apart. Worded answer for a worded question, and that one is finished.